So hello, everybody. I'll introduce myself. I'm Curtis. I'm CEO, and it's a startup. We're early stage, so when you say CEO, it's kind of silly. Think of myself more as a founder. In this case, a co-founder. I have two awesome co-founders. Has anybody heard of Cleanlab? Sweet. Okay, so a few hands. That's exciting. This came out of a grad school project, and now is used by Microsoft, Tesla, Google, Amazon. Most big companies that deal with a lot of data will find this useful, and most startups that are trying to label data or train models on data that might have errors in it will find this pretty useful. Just a quick show of hands. How many people here are here more from like the math, interested in the math, the research side? Just to get a show of hands. Sweet, okay, that's a pretty good number. Good, because there's math in here, and I just wasn't sure. And then to get another idea, how many people here are interested in how can I use this in my business or my data science team? Okay, all right, I'll try to cover both, because that was a pretty even split. So it should be fun. All right, so let's jump in. So the structure of this talk, we'll start out with how we found millions of errors across the 10 most common benchmark data sets in ML. If you haven't seen this result, this is shocking. So data sets like MNIST, ImageNet, Amazon Reviews, IMDb, the data sets that we have been benchmarking the field of machine learning on for like the last 15, 20 years, they all have errors in them. And more importantly, they all have errors in the test sets that we benchmark. In some cases, the errors are so pervasive that it actually causes the model that you find to be the best model to actually be incorrect. That actually another model would outperform that model. If you had correct test labels. So that should motivate why we want to find label errors, and then I'll show some of the ways we do that. And this was something that was nominated for Best Paper Award this past NeurIPS. The way we do this is a field called confident learning that's developed during my PhD at MIT. I worked with Isaac Chuang. Has anybody heard of Isaac Chuang? He goes by Ike. Yeah, not so familiar in ML. He invented and built the first realization of a quantum computer. And the way that you do this, it was NMR quantum computing, if anyone's familiar. And the way that you solve that problem is you're trying to get multiple qubits, you're trying to do computation, and it's a noisy signal. So you have some noisy signal, and you're trying to figure out what did the computer actually do, but all you get is noisy information. And then you figure out what's the noise process, and then you uncover what the computer actually did. And that's a very simple way to describe NMR quantum computing. So he was my advisor at MIT, and we worked together for the last 8 years or so on how do you use the same principles to uncover that noisy signal, but on data. So how can you take a noisy data set and figure out what was the noise process that made it noisy, uncover that, and actually correct that data? Then you can train a good machine learning model on it. Or you can know which of your annotators are making mistakes. So you get the idea. And then we'll talk about why this is a good idea, so why we should have AI for data correction, and then an open source tool, Cleanlab, which is one some folks in here are familiar with, where you can use a lot of this stuff for free. And Cleanlab is mostly prescriptive, the open source tool, meaning it will help you find errors, but it's an open source tool. So like actually fixing them, we'll need something else, and I'll introduce that, Cleanlab Studio. What's exciting about this talk is this is the first time ever that I've ever announced Cleanlab Studio, and we're announcing it today. So this is a complete no-code automated solution for enterprise and also for individuals to just fix data. You just upload a data set and it'll fix. And at the end of the talk, I'll show you how that looks and what that looks like. All right, so let's get started. So this was in 2016, and I was at FAIR in New York City. And does anybody know who these people are? Hopefully some. Nice, yeah, okay. So the guy on the right is Jan LeCun, and the guy on the left is Jeff Hinton. And I was young and a grad student and very excited to be in the room with them. So I'm like taking photos and trying not to get caught taking photos. And because I want them to like me and not be like, oh my gosh, this guy's a fan, not just someone working in the group. But I was having a good time, and we were working on an interesting problem. And Jeff Hinton came, and the reason I'm sharing this slide is because at this time, it gives you an idea of the state of the field in 2016. So this is one of, in my opinion, and I think many others, one of the greatest minds in machine learning, giving a talk to one of the other greatest minds in machine learning. And what is he sharing? He's sharing that he found one single error in a data set. This was exciting, to find one error. And so I've asked this question, well, how would you do it at scale? Like, how would you find millions of errors across any data set? And so in this case, this is just like an image, and the actual label given to that image is a 3. And so he's pointing at Jan LeCun. He's like, haha, you know, you gave this data set to the world, and it has mistakes. And he's just showing that he could find one of them. And so I thought, you know, hey, that data set, that paper is cited like 30,000 times. So 30,000 times someone's results, you know, and not that every citation implies the result is dependent, but for the most part, a lot of people have been assuming this thing is, you know, correctly labeled. And so I thought, hey, let's just run this through Cleanlab. And so we did a bunch of work, and there's a bunch of papers. You can check them out on your own time. But I'll just show you what we found. And so we ended up running through MNIST, and let me make this full screen so you can see. Oh, no. So this is labelerrors.com. Anyone can go to it. And here's the MNIST test set. And you can see, for example, this 9-looking thing is labeled 8. And this 6-looking thing is labeled 0. And they're kind of weird. This is a 3 or 5. It's labeled a 5. This strange thing is a 2. And so you can see there's some pretty weird data in there. And so we extended this to lots of other data sets. So we thought, hey, if anyone's familiar with like whatever, Caltech, you can see this is labeled a yo-yo, and it's like totally a golf ball. This bear is totally a teddy bear. We can look at all types of data. So I'll explain how this works in a bit. But you know, the quick draw. So this is like non-colored data, and this is an apple. Very clearly, it's labeled a T-shirt. There's all sorts of weird things. I think some people just have typos in the way this is labeled. So this cake is labeled rake. We can look at Amazon reviews. So this is something that says, you know, this book it's a little small and hard to see, but it's basically saying it's 1,300 tweets, and it's really humorous, and it's a very positive review, but the label is neutral. So they just like, when they clicked, instead of hitting the 5-star, they hit 3. And the same thing, there's an audio data set and so forth. So you can check that out on your own time and enjoy that. And so what we found is that there were actually millions of these errors. And so that was pretty interesting. This is a screenshot from MNIST. And so I looked at this across all of them, and I started to ask the question, like, what is the implications for us as a field? And so I'll quickly just go through a few things. I want to skip this very quickly because once I saw the hands, I want to get to some of the other stuff. But we use this idea of confident learning. And the idea is to find systematic errors. So if we focus on this box in the bottom left, so the idea is that a fox is much more likely to be mislabeled a dog than a cow. And just think about a data set, like there's usually a systematic structure to error. It would be, I mean, if you have totally random error, it's actually pretty easy to find the errors. Because if you had like 1,000 classes and it was uniformly random, and you had 1,000 errors, that would mean there's only one error for every class. And so you just have to find the one. You have all perfect data except for the one. So if you just have random errors, it's actually not that hard. But in real world data, you tend to have systematic error because some classes are similar, people get confused in certain ways, or the way it's annotated has certain systematic issues. And that's the type of error that we want to find, and that's what we address. And so the way we do that is there's going to be 3 equations in this talk. This is the first one, is we take this idea that if you just want to model this thing on the right, where y star is this true label, if such a thing exists. It doesn't always exist. Like, what's my true label for my emotion right now? Is it excited? Is it interested? Like, this is a noisy thing. But say that we have some proxy for like what a true label is. And then you have some noisy label you observe. So say someone labeled, you know, my current state as, you know, upset. I don't feel upset. I feel great. I'm talking to a great audience. So that would be a noisy label. Then we'd want to know what is the error rate, the probability that, you know, excited gets mislabeled as upset. And we don't actually care too much about the words that I'm saying or like the particulars about X, the data, the thing on the left. And we want to model just this sort of matrix that's going to be, if you have M classes, it's going to be M by M. So does that sort of problem formulation set up? Does it make sense? That's how, yeah.
Can you please repeat? Are you saying that X is irrelevant in this case?
It's an assumption. It's not irrelevant. X is really useful and in the actual product and in the open source. We'll do a lot of things with it. But just for this result, we'll go assume that X doesn't matter. And it's a somewhat reasonable thing to do. It's not perfect, but it's reasonable. And it's reasonable because the probability of like, you know, if you have bathtub, it being mislabeled as tub is pretty high for all bathtubs. So it doesn't really matter like if the bathtub is like an orange bathtub or a blue bathtub. the probability that bathtub is labeled just tub is still going to be like, 70% of bathtubs get labeled tub. It's like fairly reasonable. But sometimes you'll have a bathtub that kind of looks like a guitar for some weird reason. And that particular one might have a higher probability of being guitar. And we're not gonna pay attention to that for now.
Thanks.
Yeah. And so you get this matrix, which is this thing on the right. And what I'm showing here is a joint. The thing in the middle is a conditional. But if you can estimate the joint, and I'll show you how in a sec. So if you just imagine you had 3 classes, and the way you would read this thing in the bottom left, that 0.08 would mean that like 8% of your data is labeled cow. But actually, it should have been, it's an image of like a dog. Does that make sense? So that's one way you can think about this stuff. OK, so we use this formulation, and then we found all of the errors across all those data sets. And you can check this out in the paper. And I just move ahead. But I want to chat about like what's the implication. So why does this matter to you guys if you're working in ML? And this is the title of the paper if you want to look more into this. But this is just showing an idea. So on the left, you have some trained model that has 100% test accuracy, but the test set has mistakes. So those things circled in red on the left, those are all mistakes. It's where the data set actually has something that is, it looks like it's blue, but it's actually not blue, it's red. And this green thing looks like it's green, but it's actually red. So the true label is on the outside, and what you observe is the main thing on the inside. And so what happens is when if you were to measure what the true accuracy is, you'd realize, oh no, it's actually 67% accurate. So imagine this is like a car driving on the edge of the road. Like 67 is not cool. You see the problem. So that's an obvious thing. There were some takeaways from this work. I'll go through them quickly. The main thing is if you have data sets, and this is one of the things we showed, if you have just like 6% of your labels are erroneous in like a standard ImageNet like ImageNet, you can have something like ResNet 18 outperform ResNet 50, if you guys are familiar with those models. So that's like very problematic. And so when you actually benchmark it, you'll see ResNet 50 outperforms ResNet 18, but if you corrected the labels, you would see that ResNet 18 actually performs ResNet 50. The reason why that happens, by the way, is when you have noisy labels, smaller models tend to not overfit to the noise as much. And so that's why something like ResNet 18 will actually outperform something like ResNet 50 if you have like a really noisy data set. Ideally, though, you wouldn't train on that noise. You use something like Cleanlab and fix the data, and then train on good data and get a more accurate model, and then you can use ResNet 50 or whatever you want. But that's a main takeaway. And then a second main takeaway was just that we were really surprised. We didn't realize that so much data actually has errors. And I'll share a bit more about how that motivation came into play. So back to the structure of the talk. So we chatted a bit about millions of label errors. I'll dive in just a bit more about confident learning. This was a section I was thinking I would skip, but there were a lot of hands. So this is more mathier. And if someone's like really excited, if you guys are really excited, give me some indication because I have to figure out. OK. OK, great. You guys are great. OK, so I shared a bit about how we got to confident learning. And then the idea of class conditional noise. So the idea of noise depending on what the true class is of an example. Images are just easy to imagine in your mind, but this works for anything. And let's share sort of how do we do this. So this is that joint distribution that we want to estimate. And I'll show how we do it. And then remember the 0.03, the way you would read this is like 3% of your data set is labeled cow. That's a noisy label, but the true label is fox. So it's like actually an image of a fox, but the label given is cow. And if you have this joint distribution, if you can estimate this, then you can estimate anything you might need. So this is the probabilities of some true label being flipped to a noisy label. This is the prior over your true labels, which you don't even get. You don't even know that in reality, but you can estimate it from this by just summing the columns. So it's a really useful thing because it fully characterizes this type of label noise. So all you need for confident learning is 2 things. You need the noisy labels, just whatever labels you have, and you need predicted probabilities. And they should be out of sample. So predicted probabilities means you train some model on your data, and then it outputs predicted probabilities, some softmax if you're training a neural network. Or you can use, it can actually be just any logits, just any numbers, like raw outputs, and you can normalize them, whatever you want. But you need some sort of structured numerical thing over the classes that each one of them compares. Just think probabilities if you're newer to the field. So any softmax outputs are fine, and you need noisy labels, and that's it. With those 2 things, you can find the errors. And so we'll chat very quickly about how you do that. So the first thing we do is we find thresholds for each class. All right, and this is the second equation in the talk. So this thing on the right is just your predicted probability for a given example, X, and for a class J. And you only have noisy labels, so it's the predicted probability of the noisy labels, because that's all you have to train on. And they might have label errors in them, but that's what you train on. And then all this thing is a mean. It's just taking the average after summing, so it's just an average. And then what we're doing, the really key is this part here. And it's saying just look at the data that's in class J. Not the true class J, but what we get to observe, the noisy observation of class J. So say you have a bunch of images, and some of them are labeled dog. Then you take all the images that are labeled dog. And you take what is the predicted probability of class dog for all the images labeled dog. And you average all those predicted probabilities. And that'll give you an idea of how confident the model is in things that are labeled class dog. This indicates why you should probably do things out of sample. If you do them in sample, this will probably just be 1, because it's already seen the data. So even if you have noise, you won't really get any information. But if it's out of sample, and it's seen a lot of things that are dog, but they tend to be labeled other things, this number will be lower. So if this number ends up being 1, basically it means your model is completely confident in all the labels for that class. And if it's like 0.5, it's like 50% of the labels for that class are pretty messed up. That's a way to interpret this. The reason we're going to compute this is because something that was not considered previous to this work was the idea that a class can be more confident and less confident for each, or a model can be more or less confident for each class. And that's actually a real problem. It's the notion of heteroscedasticity in learning, and if you don't consider it, then you'll have some model that does really well on tigers and dogs, but really bad on keyboards, and then you'll think there's a lot of noise on keyboards, and that'll get all tricked out. So what we're going to do is we're going to normalize by the class thresholds for every class, and I'll show you how that works. So this is the final equation, and that normalization is going to occur right here with this greater than, but we're going to do it in a smart way, in a robust way. So instead of subtracting things out or dividing things, we're going to use greater than equal to. Here's the idea. So you have a class that's class J, and you get the threshold for that class. So just say J is like dog. And then you say, for a given example, okay, what's the probability of dog for that example, given that that example is actually in a different class I? So I could be like cat. So you know this thing's labeled cat, and you just want to know, is the probability of it being dog high? And how high should it be? Greater than the average, this average self-confidence for the class. And so what this does is it says it's not just high, it's higher than average for that class, meaning that there's a good reasonable notion that this thing might actually be a dog, even though it's labeled cat. And you count those things up, and you just do it for all pairs of classes. And so you have for all the things that are labeled I, and for all the probabilities of the other classes, and you can see how you can get this counts matrix. Once you have the counts matrix, you can normalize, and you get a joint. And it's really pretty easy. The cool thing about this is you can do some really nice things. So I'll show some results here. I'll see if there's one more slide I copied. I want to show you guys something really quick, actually. I wasn't sure if I wanted to do it, but I'm going to do it. So this is from, let me make this, oh, whoops. That's not good. That's okay. Living the good life. You guys see me exit out of my own talk. Nice. So I want to show just a really quick thing. This is from, this is like over a year old, but I want to actually share something from my PhD defense. And it's something that hasn't been shown, and it's just really cool. I think you guys will dig it. Yeah, who does this, right? But I'll show you why, because it's kind of fascinating. So when you see a formulation like this, your gut is probably asking you, like, why do I trust this? Like, cool, it seems reasonable, it seems very simple. And I've made it sound very simple because I've spent like 8 years thinking about this problem. But like, why should this work? Why is it good? So let me just show you. If the probabilities of the model are wrong, you'll still get the right answer. And so that's what I want to show you right now. So this is just a quick intuition. So we've seen this equation, and we've also seen this equation. So this is the two things I showed you. And the idea here is, what if your model is actually wrong? Like, it gives you wrong probabilities. Will you still exactly find all the errors? And the answer is yes. So I'll just show you that really quickly. So just assume that if you had if a model that was perfect, meaning every predicted probability that came out of the model was exactly what it should be, just take for granted that this method will exactly find label errors. And you can look that up in the paper if you just search confident learning. But now we're going to make that worse. We're going to say the model can be wrong for every class. So for every class, you can add some error. It can be like +3 to all the probabilities or -3. And we go further, but this is a simple one and easy to show, and it's interesting. So here's what we're doing. Right here, we've added an error term per class J, meaning that the model actually it's overconfident. So the probability for this class J is too high. When you recompute the threshold, you're going to get the threshold plus some error term. So if everyone's following, it's just an average, and you've averaged in a sum of a bunch of things. So that sum drops out. And you can look at that for a sec if you need to. So your new threshold is just the threshold plus whatever the overconfidence is. Okay? And now let's just look at our confident joint, this thing when we're counting up all the errors, and let's see how it's affected. So now our new threshold is the threshold plus that error term. And our predicted probabilities that we're going to compare to that threshold is the predicted probabilities plus that error term. And let's just see what happens. The error terms will drop out. And so now you get the original formulation, which we already know works for perfect probabilities. So we know that even when you have this error, you're still going to get the exact results for perfect probabilities. That's it. It's really simple. And in the paper, we go a lot more complicated. So in the paper, you can see how this actually is true if you have noise in every predicted probability, not just every class, at the individual level. So that's just a fun intuition on why this formulation is a reasonable thing to do. And now let's look at some cool results that we can get out of it. So skipping to here, just some quick benchmarks. This is like the proverbial table. It's like required for a talk like this. So there's a whole bunch of works that have done noisy learning stuff in the last few years. And I've just made it simpler. So some confident learning stuff at the top. And then there's some other works at the bottom. And there's a few things that are really interesting here. So over here on the left, what we're doing is we have that joint matrix I showed you. But then there's two kinds. One is where most of them are 0, meaning there's nothing flipped in that class. And that's realistic. That's the way it is in the real world. In the real world, you have, like, say, 10 classes or 100 classes. And most of them aren't actually mislabeled as other things. Like, a bathtub is not usually mislabeled as a lion. That doesn't really happen. But if you look at a lot of works, when people study this thing, when they approach this problem, they'll do these joint matrices with error in every single term. And that's just not actually how it is. In the real world, there's lots of zeros. I call that sparsity. So on the right, what we have is 60% sparsity, meaning 60% of that joint, the off diagonals, are 0. So that's more realistic. And let's see what happens when we look at these confident learning methods. In this case, we had 40% noise on CFAR, which is a standard benchmark data set. And what you see is that as you go to the right, when you increase the sparsity, meaning make it more realistic, you get this drop off in performance with most methods. And that won't happen with confident learning. And that shouldn't surprise you too much, because we're actually modeling this joint matrix directly. We're doing what the problem would like us to do. And so we're finding those errors. We know that most of them are 0 already, and so we take that into account. So that's one good benefit. There's something else that I just want to share. Who here is sort of interested or curious, or maybe you think it's all, it's not really like a real thing, but just interested in the whole data-centric AI movement and people being excited about data-centric AI. Is there any belief that that's a good thing? Cool. OK. This is something that hasn't been shown. It hasn't been published. But it's a really cool thing. If you actually just look, these are ranked by how accurate they are on a test data set with no error in the labels. We just ranked performance by training using various learning with noisy labels methods. And then we see how do they perform on a true test set? How do they benchmark? And what we found was that the models that are model-centric approaches, meaning they modify the loss function or they modify the model, tend to do worse than approaches that modify the data directly. So things that either take data and join them together so that the noise is sort of averaged out, or things that clean out data, or things that take samples so that you have less error in each sample. Basically, taking a data-centric approach was shown to outperform taking a model-centric approach. It's like a perfect divide. And that's just kind of cool. So if you're into data-centric stuff and your friend's like, I don't know, it just sounds like a buzzword, there actually is good reasoning behind why this is a good idea. OK. You guys with me? How are we doing? Cool. OK. So we're at the 25-minute mark, and this is a 35-minute talk. So I want to leave 5 minutes for questions. So I'll go over the last two things pretty quickly. I was going to share a bit about how this whole grad student project became a company. And how does Google end up using it and Amazon end up using it? And what are the use cases? And there's a lot. The brief of it is in like 1 minute. I really cared about, I'm from rural Kentucky, and my mom works in a call center. My dad was a mailman. And so I really wanted to sort of do a lot, but I couldn't. And so I thought, how do we empower people? And so I went to MIT, and when I started out, I was using ML for education, to democratize education. You guys heard of Coursera? Or, OK, sweet, edX. Slightly less known, but similar. So the idea was to have edX let anyone in the world earn a certificate from MIT or Harvard and then be able to work anywhere they wanted, no matter if they're from rural Kentucky, where I'm from, or if they're from Africa or India, or wherever. That was the idea. The problem was that people were creating 2 accounts. And on one account, they were clicking show answer, copying the answer, opening up a new window, making a new account, and just pasting it and earning a certificate without knowing anything. And then they were getting jobs. And then they couldn't perform in those jobs, and people were like, oh, these certificates are meaningless. And it just ruined it for everybody. And so what I spent my first 2-3 years at MIT doing was building MIT and Harvard's cheating detection system. So I actually spent like 3 years training my mind on how do you take a bunch of data and find the errors in it. In this case, certificates, which ones were cheated. And then I tried to train a machine learning model that would do this generally for any course. And I was going to deploy this into all of Harvard and MIT's online courses. And when I tried to do that, I ran into a tricky problem. There was actually no solution in machine learning for learning with noisy labels. And that's how we got started. And so that's when I started building confident learning. And then I went to Jan LeCun's group, and we found out that actually Facebook needed to solve this problem. And then went to Amazon and realized, oh, Amazon needed to solve this problem. And then Google needed to solve this problem. And I spent 2.5 years at Oculus. Oculus needed to solve this problem. And I spent summer at Google, and Google needed to solve this problem. And all the while, I'm using Cleanlab and improving Cleanlab. And so that's sort of how it happened. And you can read more about that. So I'm going to skip this for time, but we use this for the Data-Centric AI competition. Andrew Ng's competition is really useful. And jump right into the open source. So for people who just want to use this for free and you want to use it on your own, you want to find issues in your data, you want to find label quality, it's on GitHub. Anybody can use it. It's open source. You can see the code. You can see how the algorithms work. It's all there. And then just a quick thing. If you have your own data set, how would you do this? It's just 1 line of code. So you would do import Cleanlab, and then cleanlab.classification. And then we have this thing called clean learning, which is like machine learning, but on clean data. And then you would just pass in whatever model you want. It's scikit-learn compatible. If you use PyTorch, then you can use something called Scorch, which will make your PyTorch model Scorch or sklearn compatible. And then it'll also just work with any model, and you can look that up in the GitHub. But you just pass in whatever model you want, and then you would call .findLabelIssues. You'll find all the errors. And it'll print out a nice data frame. It'll show you what are the errors for each of your indices for each of your data. You can check that out. And so the last thing I want to show is what I'm excited to announce, which is how do we do this with no code? And how do we do it automatically and in a way that's enterprise ready? And building this was hard. We spent like 9 months working on it, and this is the first time we're sharing it. I'm pretty excited to share it with you guys. So let me just show you really quick. So some things that we wanted to achieve is how do we do this in an automated way? No code, so anybody can do it. 1 click, so a nice interface that feels good, so you can just press a button on your keyboard, and it will just like check data or fix data, and it doesn't feel hard. And then finally, we want it to be data agnostic, so it should work with any type of data set. And what our current deployment does is it works for text and tabular data, and then we have image and audio data coming this fall. So I'll just show you really quick, Cleanlab Studio. If anybody wants to check this out, cleanlab.ai/studio, you can check it out for yourself. So the idea is you just have some text example, and it has some label. You just run it through Cleanlab Studio, and it will like give you an idea of what the true label should be. And then there's a few examples. All right, and then folks who are using Databricks, it's a simple integration. You can just send an email to team@cleanlab.ai, and we'll set it up for you. But anything that's like Parquet or Lakehouse, however it's formatted, in the back end, all we're doing is we're just converting to CSV and then uploading it. I'm not supposed to tell you that, but it's what you would expect that we would do. But it's really easy integration, and you would just click deploy on Cleanlab and then open up on Cleanlab. And so I'll just show you starting from there. So what you do to upload a data set, actually for time, I'll skip this. This is just uploading. It's really nice. We do a lot of data profiling stuff, but I think for time purposes, what you really want to see is like the actual cleaned data. But just it works for text, tabular data, and I'll just show you. It'll find all the fields for you, and then you can click this. We support light mode and dark mode because everyone has to do that. And then I'll just show you really quickly. So folks who have used data profiling tools, it will do this for you. So if you have any errors, like if any values are missing or if you have duplicates, it'll just find that for you and tell you where they occur. And you can just download that and use that if you want. Once your data set is uploaded, then you can create what's called a project. And in a project, you can do a few things. You can upload those predicted probabilities I already mentioned if you want to use some weird model, or it'll just do it for you. So we'll also train a model for you using a bunch of AutoML. A fun fact, our chief scientist at Cleanlab is Jonas Müller. If anyone's heard of SageMaker, AWS SageMaker, that's built, awesome. Yeah, it's built on AutoGluon for their AutoML. AutoGluon is an open source deployment for just AutoML anything at Amazon. And Jonas Müller was the lead architect of that. He was one of the lead developers for 4 years and then joined us just recently. Good friend, good guy. We did our PhDs together at MIT. So now let me show you without sort of further ado, let me show you Cleanlab Studio. So once you have a data set ready, the project will just run and it'll say, can you guys see this? How blurry is it on the screen? Oh no. Let's see if it's a Wi-Fi thing. You guys are great. Super helpful audience. Is it good? 720? All right, sweet. So this is a real data set. This is a tweets data set. It's from public data, so that's how we're okay to share it, but this is like a real data set. And what you can see is the interface. And so I'll just sort of talk as my mouse is moving. You can make it bigger and smaller, that's all I'm showing. But there's a few things that you're gonna wanna do. First of all, you wanna know how many issues were there in your data set right away. And then what is there sort of left to check if you want to resolve them. You can just auto export, by the way. You don't have to check them yourself, but if you want to, we make an easy tool to do that. And then what this is showing is just standard tools you would expect. If you're gonna interact with data, you need data interactive tools. And so just showing you that you can select which columns, that should be an expected thing. You would expect something like this to support. And then some filtering, like say you only wanna look at the rows where the text contains the word sure, just as an example, then you can do that. And that might be useful if you're like interacting with data or finding that there's weird things in data in order to sort of hone down on what you're interested in. But without doing that on your own, this will be done automatically. So the quality is ranked. So every single example is automatically ranked by a quality score. And that quality score is based on the data distribution and also the label. So this is a quality of how accurate that label is for that example. And you can just sort your data by that so that you don't waste time looking at stuff that's like correctly labeled. And you only start with the things that are most likely to be erroneous. On the right, we have these actions. I'll show you how that works in a second. In the beginning, the things that we think are errors are gonna be unresolved. And then you'll take actions to fix those. And then finally, we have things like issues. An issue means that we think there's an issue in the label, and we recommend that you take a look. And you can sort by issue to see which things you look at. So here I'm looking at the first example with the lowest quality, and it says, we're hung up on twice. And the label given for this was neutral, which is clearly a problem. And so you can see our suggestion in the bottom right. And it'll tell you what our suggestion is, and then it's just a single key press. So if you check in the bottom left of this video, you'll actually see the buttons I'm pressing display on the screen. So for example, up and down lets you see different examples. And then if you want to fix or change or check an example, it's a single button key press. So here you're just pressing W and it just uses our suggested. In this case, I think the actual thing is correct, that it was positive. And so you can press keep, that's the Q button, and you're just working through, and so you can check it. You don't have to do this, but we recommend it. If you really want like the perfect quality, then it's unlikely that a machine learning solution is going to give you 100% perfect. What we're going to do is order it for you, so it's really easy, and then give you what we think is a suggested label, and you can totally just export that and move on. But if you want that 100% perfect quality, then we recommend you check it. And so we try to provide really easy tools for you to do that. This is an example of something that hasn't been checked yet. So the action is unresolved, and we take a look at it. I missed my flight. It was actually a weird example. If you look at this example, it's like very strange, a very strange example. This one, yeah. So this one is saying, after missing my flight, I ended up walking to another flight, and my phone is still on the seat. So it's weird. It's like, did this person leave their plane, and then they went to another plane, and the phone they left in the previous plane is on the next plane? Because that would mean that this is a wormhole or something. So it's very weird. And so the way that you might have weird stuff in your data, and so we allow you to just exclude it. And so that's what this is showing, is just like press E and just get that out of there because that's like very strange. I don't know what the sentiment would be with that. So you can see the idea here, and then there's a few other things to show you, just moving to the very end. At the end is all the like high quality stuff, and you can check this. This is all stuff that's labeled negative, and it's like super clearly labeled negative. But when that happens, you'll notice there's no suggested label. It'll just be keep the given label, and if you want to relabel it something else, you can always do that. And then in the bottom, you can always rerun Cleanlab. Once you've made it more accurate, then you can train on the more accurate data, and we'll give you even better quality scores. And that's so you can do it iteratively within the app, or you can just export your data, dump it back to Databricks or as a CSV. So that's how we do it, automated with no code, and that's Cleanlab Studio. I hope that was interesting to you guys. Yeah. Yeah, the only last thing is just a slide that shows sort of the 3 links. So there's sort of these 3 guys. Check out labelerrors.com, open source is in the middle, and Cleanlab Studio at the end.
You want to take questions?
Yeah, I can take questions as long as you guys want to have me on stage.
Thank you for the presentation. That was fantastic. For the Cleanlab Studio, what do you support in terms of like what you're able to like, what type of data you're able to see? You showed text right there. Do you also support seeing like pictures? And then another data set that I particularly have is like a 3D point cloud where I actually interact with that point cloud while making the label. Would you support like adding kind of custom like JavaScript visualizations in that area as well?
Yeah, totally. So the way it works right now is if you want to use, so Studio supports text and tabular today. We're doing image very actively right now, and it'll be ready in the fall. And we'll add audio. We haven't seen as much interest in audio, but that's coming also in the fall. And that's pretty easy for us to add. So images in the fall. If you right now want to start using Cleanlab, and we don't support images yet in Studio, there's 2 options. One, we have a wait list. You can sign up and you'll just get notified. But maybe you want to just get using it today, and that's not very helpful. So then try the open source. With the open source, even for your point cloud solution, if you have any model, it doesn't matter. Because remember, Cleanlab just uses the predicted probabilities and the labels. So we actually don't care what the model is. You use your predicted probabilities for whatever. It can be 3D. It can be any problem. And then you have your labels. And then you can run that through the open source. And that's a good way to get started. And you can build whatever you want to on top of that. You know, it's open source.
Hi there. Quick question about, well, does your framework work with binary classification problems? Because I see how you key in on multi-class classification, right? And then how you extract the error from there.
Yeah.
Then I'm curious about binary, because for me it's important. It's fraud prevention, and then I only have fraud or non-fraud. And
yeah, totally.
Yeah, I have like a 5% estimated false positive rate in there, and I'm curious of how to extract those noisy labels. Yeah.
Yeah, totally. So binary is really easy for us. It's the easiest problem for us. And it's how Cleanlab initially got started. Remember I was trying to detect if a certificate was a cheater or not? So that was actually the first problem that we did. And that was the origins. And the reason it's really easy to solve is because that joint matrix, the diagonals are just how accurate are each of your labels. But then you only have 2 noise rates, you know, false positive and false negative. So you only have to estimate 2 things. And then once you know those 2 things, you can figure out how much noise there is total in your data, and then rank data, and only take like the top number. Say it's 100, you find 100 errors, then you would rank it, find the top 100. It's actually a much easier problem to solve. And so I feel pretty confident, you know, standing here telling you, like, definitely use Cleanlab for binary solutions. If you have a decent model, it'll work really well.
Oh, hi. So I think you've showed it. I just never quite got it. How did you estimate the, I forget, the confusion matrix again through cross-validation? Or?
Yeah, totally. So the sort of overall idea is you think of an example, okay? And then what's the probability? Say it's labeled dog, okay? What's the probability of dog, given that it's labeled dog, okay? And then you have a class threshold for class dog. And if it's not greater than that, it might not be dog. But maybe its probability of cat is actually greater than the class threshold for cat. Now it's likely to not actually be labeled dog and likely that it should be labeled cat. And then you could do that for all examples.
I see. Is there a, like, did you do a study or anything like how, if, to what degree your labels are like mislabeled, how much that would cause the algorithm, the assumptions to break?
Yeah, so it depends on the model. So if your model is less than 60% accurate and you have more than 40% noise, it gets really hard to disambiguate what's called aleatoric and epistemic noise. So you have an intrinsic noise in your model, and you've got noise in your labels, noise in your data. And the thing is, when you're training, those are mixed together. You have to disambiguate them. One of the ways we do that is by taking that assumption, that class conditional noise assumption, that gets the X out of there. If you leave the X in there, then the probability ends up looking very similar to the model. It's a mathematical argument, so it's hard to say on stage. But basically, you need to disambiguate these two types of noise. And if your model's really bad, then you're going to do poorly. Another example where things can get tricky is if there just really is no true label. And I tried to mention that earlier in the talk. But otherwise, those are sort of the two edge cases and where things can go really bad. If you have a good model, you should be OK.
Great, thanks.
So we're out of time. Are you willing to take more questions?
Yeah, I can chat on the side or wherever.
Side? Awesome. Thank you so much. Remember to rate this session. Appreciate your time.